Here we go, acylation of amines. So this is something that we looked at a lot earlier on when we were talking about amines, and we did this in the carboxylic acid section as well. We said, okay, well, if you take an amine and you treat it with an acid chloride, we need 2 equivalents of the amine for every 1 equivalent of the acid chloride, right? Because you end up with HCl, and then of course the HCl is going to react with the second equivalent of your amine, right? And that's going to give you an alkyl ammonium salt, which is going to prevent HCl from doing any funny business. And so 2 moles of the amine, again, are required for every 1 mole of the acid chloride. But it says that acylation of an amine can be used as a protecting group. Remember we talked about protecting groups of alcohols, for example, when we talked about Grignard chemistry? Well, now we're going to talk about protecting an amine and why you would want to do that. And this kind of takes us right back to our electrophilic aromatic substitution reactions, because you remember earlier on, we talked about this reaction that's shown here. We said if you take aniline, and if you want to do a bromination on aniline, you cannot do a monobromination just by taking it and treating it with bromine, because this is such a strong activating group. So strong activator. And what that does is it results in polybromination. And so again, it's because the amine is such a powerful activating group. So what we're going to see is that we can convert this to an acylamine, and then that's going to mitigate or lessen the activating power of the group. Let me show you what I mean. If you start it with aniline and you treat that with acetyl chloride, okay, so this is just acetyl or acetyl chloride, however you want to pronounce it, okay, depends on where you're from probably. Anyhow, acetyl chloride, we take that and we make acetyl aniline. Okay, well, once we have that, now you've got an amide on here. Is this a good directing group? Sure, but it's a moderate activator. So now we've got a moderate, okay, activator, which is going to be orthopara directing, but the ortho positions are going to be mostly blocked because of the free rotation around this bond. And so that's going to activate any kind of substitution reaction into the para position. And so if you just treat this with bromine, then you get parabromination. Well, how do you hydrolyze this bond? You can do it in acid or base, doesn't matter. Okay. Now, I would choose to do this in base because then you end up with the aniline. It doesn't say it here, but if you were to try to hydrolyze that in acid, you'd end up with the salt. So you'd have to treat it with base again. But whatever. The idea is that you're using the amide or the acetylated amide, or the acetylated aniline, I should say, to make an amide, which is going to be basically moderate the reactivity of the aromatic ring. The disadvantage is that you know the hydrolysis of an amide requires harsh conditions. Okay, it's kind of a tough reaction. You really got to beat up on the reaction. So we'll say, again, here you can use sodium hydroxide, or you could use acid, and I'm going to add here followed by base. You'd have to do that. All right. Well, remember another thing we talked about, if you have an aromatic amine, so if you have an aniline, that you can't do Friedel-Crafts chemistry on it. Remember that Friedel-Crafts alkylation or Friedel-Crafts acylation? Why? Because you need a Lewis acid like aluminum chloride, okay? So aluminum chloride, AlCl3. Well, aluminum chloride is a Lewis acid. What's a Lewis acid? It's an electron acceptor. So it's going to react with the lone pair on the nitrogen of your aniline, and it's going to form this. Now your ring is totally deactivated, okay? So that's not going to allow alkylation or acylation to occur. So you might already see where I'm going with this, and that is if we were to acylate the nitrogen first to make the N-acyl aniline, then we can do our Friedel-Crafts chemistry, because now the nitrogen is not going to complex with the Lewis acid, and so we have a moderate activator. We can do our Friedel-Crafts, and then we can remove the acyl group. We can either use sodium hydroxide, or we could use watered followed by sodium hydroxide. So again, the same thing applies. Harsh conditions for the hydrolysis, but hey, it'll work. So these are the 2 examples of when you've got to know to do the acylation of an amine. So very specific examples. Let's take a look at some practice problem. It says here, when aniline is treated with nitric acid and sulfuric acid, so if we take aniline and we take that and we treat it with nitric acid, HNO3, and sulfuric acid, H2SO4, okay? The expected nitration product, para-nitroaniline, so that would be this guy, okay, where you have the nitro group here. Come on. It says it's obtained in a poor yield. Instead, the major product is meta-nitroaniline. So instead of getting this, you end up with this compound where you have the nitro group here, okay? Apparently, what happens is that the amino group gets protonated under these conditions, and then you end up with an ammonium ion. So you end up with the anilinium, which looks like this. Now you've got a deactivator, and where do deactivators direct to? They direct to meta position, okay? So apparently the amino group is protonated, resulting in an ammonium group, which is a meta director rather than the ortho para director. So it's asking us to propose a plausible method for converting aniline into para-nitroaniline. And so you can probably see where we're going with this. What you would want to do is that first you would want to acetylate the nitrogen of your aniline. Why? Because that's going to mitigate its reactivity. If we treat it with acetyl chloride, we end up with the acetyl group over here. And now it's a moderate activator, but it's still an ortho-para director, and it's going to be most activating to the para position because of the free rotation around this bond. So now if we take this and we treat it with nitric acid and sulfuric acid, so let's do that. We got HNO3 and H2SO4. We're going to nitrate in the para position. So we've got our nitro group here. Still have our acetyl group, and you know how to remove that. Okay, we've talked about it a few times. So now we can just blow that off. I'm going to use sodium hydroxide because it's only one step. Even if it's a sluggish reaction, it'll still give us the product if we wait long enough. And maybe if we heat it up enough. So we end up with para-nitroaniline. And so that is a perfectly reasonable synthesis of the desired compound. In question 22.1, it says starting with nitrobenzene and using any other reagents of your choice, outline a synthesis of para-chloroaniline. So if we start with nitrobenzene, okay, and we want to make para-chloroaniline, okay, and I can see what they're getting at here. If you have para-chloroaniline, it might be a knee-jerk reaction to say, well, I'll just reduce this, okay? I'm just going to reduce this using HCl and zinc, for example. That's going to give me aniline, and then I can just go ahead and chlorinate that with Cl2. But the problem is, not only will you end up with the chlorine there, but you'll get polychlorination because this is so strongly activating. And so, just like the previous problem, we want to try to mitigate the reactivity of the nitrogen on the ring. So, we're going to start with our nitrobenzene. And in the first step, yes, we are going to reduce it. So I'm going to use, and I should have put HCl and zinc followed by sodium hydroxide. But anyhow, whatever. I'll reduce it using HCl and zinc. Then I'll treat it with sodium hydroxide to make the free base. So I have my aniline. Then I'm going to treat that with acetyl chloride. So that's going to put in the acetyl group. Now I've mitigated the reactivity. It's still an ortho-para director, but it's not nearly as reactive as aniline. I treat that with chlorine. That's going to put the chloro in the para position because it's the less sterically hindered. And then to remove my acetyl group, all I have to do is treat that with sodium hydroxide. There you go. And that is going to give me, come on, the final product, which looks like this. Oops. Which looks like this. There we go. And there we go. And Dunsky. Just like that. Kind of a cool synthesis. And, you know, it's not a big reaction, you know, just acetylating. You know, really all we've learned is this reaction, which is a reaction that you've already known. Everybody here could write the product of that reaction. It's more, you know, 22.8 is more about what would you use it for. right? When would you use it? When you want to do a Friedel-Crafts, you would use it. And when you want to do a halogenation in the para position, you would use it, okay? And those conditions. And why do you have to use it? Because if you try to just straight up do the chlorination or the bromination of aniline, you end up putting chlorines and bromines everywhere, all over the molecule, okay? If you try to do a Friedel-Crafts on just plain old aniline, right? Where was it? Back here. You end up making this and it just doesn't work, okay? Basically, it ruins the reactivity. All right, so kind of cool stuff there. Well, let's look at one more section. You guys remember way back in Organic Chemistry 1, we used to talk about the Zaitsev product and the Hofmann product. Like, let me show you an example. If I just draw, this compound down here, okay? So if you were to treat that with, say, I don't know, sodium methoxide, right? You'd make this compound, and we call that the Zaitsev alkene. But remember that we talked about what would happen if you were to treat this with potassium T-butoxide. In that case, you'd end up with 1-butene, which is the Hofmann product. So Hofmann, I always forget if it's 2 F's or 2 N's. It's 2 N's. Anyhow, you get the Hofmann product. I can make it a little bit cleaner than that. But the whole idea behind Hofmann elimination is that you're just ending up with a less substituted alkene. So what it's saying here is that, sure, you can use a hydroxyl and convert that into a good leaving group. How do you do that, right? First, you would treat it with tolusyl chloride and pyridine to make the tosylate. Then you would treat it with, sodium methoxide or whatever to do the elimination. Okay, great. But what do we do with an amine? How do we convert that into a good leaving group? Because it is not a good leaving group by itself. And what we're going to use is something that we looked at earlier today, and that's called exhaustive alkylation. Let me show you. If you use excess methyl iodide, so excess CH3I, it's going to convert that amine to a quaternary ammonium salt, right? You make a quat, and then you've created a good leaving group, haven't you? Right? Think about it. If that gets attacked by a nucleophile, or if you just did an elimination reaction, for example, if you had a strong base come along, and rip off this proton, like, you've got a good leaving group, okay? You're going to lose an amine. That's a good leaving group. So the strong base is going to cause the E2 elimination. What do we use for a base? Well, this is one that you probably haven't thought of, but you end up using silver oxide. So remember, it's not silver 1 oxide, it's just silver oxide. Silver only has 1 oxidation state. So we use silver oxide. So what would be the step? First, you would treat the amine with excess methyl iodide. Then you treat it with silver oxide in water, and you heat it up a little bit. And you end up always with the Hofmann alkene, okay? The less substituted product, okay? And again, the reason why is because you convert this to a good leaving group. So we call that the Hofmann elimination. Now, the purpose behind the silver oxide in water is to convert, basically to convert the alkyl iodide salt. So I don't have it drawn here, but it's basically to take this compound, which I should have given myself a little bit more room, but you've got your 3 methyl groups on here like this, and then you'd have the iodide after the first step. Then you treat it with the silver oxide in water and you heat it up, okay? You basically exchange the iodide for a hydroxide, so you end up precipitating silver iodide out of the solution, and then you end up, so this is a solid, and then you end up with the base, and the base does the E2 reaction to make the Hofmann product, okay? And it's important to know that even from, what you learned in Organic Chemistry 1, it's consistent. The Hofmann eliminations give the less substituted alkene, okay, in terms of regiochemistry. Now, come on, this is Organic Chemistry 2. We got to have a reason, right? I got to give you a reason why you end up with the less substituted alkene. Well, it's nothing more than, and I'm never going to ask you to draw the Newman projection of what's going on here, but it's basically, if you try to do the elimination to make the Zaitsev product, rather, if you look down the carbon-2, carbon-3 bond, in order for one of these protons here on carbon-3, in order for one of those to be anti-periplanar to the leaving group, you end up with a gauche interaction, okay? Whereas if you do the Hofmann elimination, if you remove one of these 3 protons, you can have a conformation where there's no gauche interaction. Okay, it doesn't exist. Okay, and that's the answer. It's nothing more than that. I don't even think there's a question in the suggested practice problems that I assigned where it asks you to draw the Newman projection. If there is, it might be 1. But what you need to know as a Chemistry 3111 student is that you make the less substituted alkene. So it says here, draw the major product that you expect when each of the following compounds is treated with excess methyl iodide followed by aqueous silver oxide and heat. So we're starting with cyclohexylamine. So that's like cyclohexanol, but it's cyclohexylamine, okay? We're going to treat that with excess methyl iodide. I'll draw the whole damn thing out here, pardon my language. So let's move this over here. Okay, what are we going to get in the first step? We're going to end up with this guy. So we've got 1, 2, 3. So now it's got a positive charge. We have our iodide over here. Then in the next step, you're going to treat it with silver oxide, water, and you're going to heat it up. And that's going to do an elimination to make the Hofmann alkene. Well, in this case, this is your alpha carbon, your beta carbon. There's only one kind of beta carbon, so there's really only one possible answer here. There isn't even a Zaitsev product that could be formed. This is both the Zaitsev and the Hofmann product all at once. But the next one is a good example. If you were to start out with R3-methyl-2-butanamine, so that would be this compound here, like this, okay? If you were to treat this with excess iodomethane, followed by silver oxide and water, you cook that up a little bit. If I draw a line here or a line here, can anybody tell me where you're going to make the double bond? Would it be where the yellow dash is, or the yellow highlighter is, or the green highlighter? If you're going to make the Hofmann product, it is not me trying to trick you. Which one would get exactly? Thanks, Skylar. It's where the green one is. That would give you the Hofmann product. So you end up with this compound. So that's 3-methyl 1-butene. Okay, nothing more than that. The last one, again, in the exact same vein, you have N-dimethyl 1-phenyl propane 2-amine. So look, you do propane. Okay, you've got, son of a gun. You do propane. You've got an amine on the second carbon. Okay, you've got N-dimethyl. And then you've got a phenyl on the first carbon. So there you go. There's your starting material. Okay, you're going to treat this one with excess methyl iodide, followed by silver oxide, water, and you cook that up. And you do the Hofmann elimination. Now remember, you're going to end up doing the exhaustive alkylation like this, okay? But you look and you've got 2 types of beta protons, right? You've got betas here and you've got betas here, but you're going to rip off the one that's where the green beta is to make the less substituted alkene. So you would end up with this compound where you have your aromatic ring and then 1, 2, 3. There you go. And your double bond is right there. And that's your Hofmann product. So we'll stop there for today. And then next class, we're going to start by taking a look at reactions of amines with nitrous acid.